Welcome to lesson 32 class. So for this lesson, we will discuss design of storm sewer to carry the peak runoff. The peak runoff we calculated either using the rational method or NRCS method or hydrograph method. So basically now we will design a storm sewer to carry that peak discharge. You will be happy to know this is the last class material for this water resource engineering. Yay! But we will have few other classes also where we will discuss about the test 4, and we will do some review for test 4, and I will explain those in details later. So let's start today's lesson, design of storm sewer to carry the peak runoff. So before starting the designing of sewer system, we need to know what is actually the drainage system, because the sewer system, that is a part of drainage system. So the drainage system, you already know that it's a system to remove the excess water so that people's life and properties like that will be safe. Now, there can be different type of drainage system. It can be urban drainage system, it can be agricultural drainage system, roadward drainage system, or airport drainage system. But for this class, we will only discuss the urban drainage system, because stormwater sewer system, that is a part of urban drainage system. And for urban drainage system, there are two parts. One is the sanitary sewer system, which carry the wastewater from household, commercial, and industrial buildings or companies. And another one is the stormwater sewer system, which carry excess surface water after rainfall, basically the runoff from roofs, yards, streets, or any other surfaces. So for our class, we will mainly discuss this one, and this picture will help you to understand what I meant by stormwater sewer system. Since we will know the peak runoff, so we need to design some pipe network like this one, which can carry that amount of water, like the runoff. So basically, we have to find the diameter of this pipe, because for stormwater sewer system, most of the time pipes are circular. So basically we have to come up with the right diameter for the pipes here. Okay, so that's what we will do in this lesson. So for designing that one, there are two steps. As I said, the first thing is we have to determine the peak flow or peak runoff, which will act as a design discharge, okay, and which is produced by a precipitation storm of a certain specified return period, referred to as a design frequency. It's like after how many years we can expect that rainfall. Okay, so for storms here, usually the design frequency is 2 to 10 years. And once we know the peak flow, the next one is we have to find the sewer size or diameter to pass this design discharge. So these are two steps. And there are some limiting conditions, like we can use different pipes and everything, but we need to make sure that the minimum velocity inside the pipe, it will be 3 feet per second or 0.9 meter per second. Basically for self-cleansing velocity, that means to make sure there will be no deposition of like particles or something like that. And the maximum velocity is 15 feet per second inside the pipe, because if the velocity is more than that, there can be scour, or maybe the pipe will not serve as till its design period if the maximum velocity is more than that. So when we will design, or when we will select the diameter, we have to make sure that we are checking the velocity as well. So Our last class example for this course, which is class example 26, it gives us a scenario from where we have to design the pipe size. So let's read the question. Determine the size of the concrete pipes. So the material is already given of n, Manning's n, 0.013 for a 10-year storm, that is the frequency, if the pipes are laid at 0.4% slope. So basically that is the bed slope, or the slope like on which the pipes will be laid down here. That is the slope. Given that minimum time of concentration TC is 15 minutes, like for each area, and the rainfall intensity is I equals to some equation, where TC is in minutes and I is in inch per hour. Details of each sub area is given below. So basically you have to find D1 and D2 from this scenario. We have area 1 and area 2. We know the C1, C2. We know the individual time of concentration for each area. So we have to find the diameter 1 and diameter 2. And they already gave you the commercially available round concrete pipe size. So we can choose the pipe size from this table, and we can check the velocity. And at the same time, we have to check whether this pipe size can carry the peak discharge or not. Okay. Now, one thing here, when we did the rational method, we found the I from the IDF curve, like intensity, duration, frequency curve. But this time we have an equation. So if we have the IDF curve, we can use that. If we have the equation, we can use that as well. So based on what is given, that's how we will actually calculate the rainfall intensity. Okay. Now let's start working on that. If you look at your class example, you will see I typed some steps so that you can follow. So I will follow the same steps. The very first step is write down the given values and limiting conditions. What we usually do for any class example. So all the given values are here. And for find, we have to find the size of shear D1 and D2. And there are few limiting conditions, though the minimum velocity and maximum velocity is not given in the question, but we already know that, which is the minimum velocity is 3 feet per second and the maximum velocity is 15 feet per second. And the another limiting conditions was minimum time of concentration 15 minutes for each sub area. Now, if you look at the question, you will see the time of concentration for each area was given. Still, we have a minimum time of concentration 15 minutes. That's because for some county, they fixed the minimum time of concentration so that in calculation, engineers don't get too much peak runoff, because that is sometimes that is misleading value. So that's why they fix a minimum time of concentration for each area. So for this area, minimum time of concentration is 15 minutes. Now step 2, calculate peak runoff discharge using rational method. It can be any other methods also, but obviously the total area, if you look at that, it's below 15 acres. So we can use the rational method, and that is widely used. So for rational method, the equation was Q equals to CIA. We know C is the runoff coefficient, I is the intensity, and A is the drainage area or watershed area. So for this one, since we have to find D1 and D2, at first we will find D1 and then we will start working on D2. So for D1, if you notice, the water is coming from actually this area, right? So for D1, if we want to calculate the design discharge or peak runoff, The drainage area will be 5.3 acre, which is given here. Dimensionless runoff coefficient 0.2. So we have to calculate the intensity 83.83 TC plus 12.5 to the power 0.89. Now the TC was in minute and I was in inch per hour. Now the TC is the time of concentration. So how many different time of concentrations we can get from this area 1? Let's look at that. There are two possible time of concentration. The first one is 13 minutes, which is given, but there was a limiting condition that the time of concentration should be at least 15 minutes. So in between these two, obviously this one is the larger one, and we know from the definition that we will always take the largest value for time of concentration. So for this TC, we will use 15, and now the I is 4.39 inch per hour. And if I if I give all the value on this equation, our design discharge for this area is 4.65 CFS or cubic feet per second. So basically this pipe or this sewer has to carry 4.65 cubic feet per second of flow. Okay. Now step 3. Now we have to select the diameter. Select pipe size to carry the peak discharge and calculate discharge for pipe flowing full using Manning's equation for the chosen diameter. Okay, and as we said, when we will choose a diameter, we have to make sure that pipe can carry the peak discharge here. At the same time, it can maintain the limiting velocity conditions. Okay, so from our previous calculation, we know the discharge is 4.65 CFS. And since this is the commercially available pipe, we will choose a pipe size from this table. The first one is 12 inch. Let's work with this one. So if I select D1 equals to 12 inch or 1 feet of pipe, I have to find what amount of water this pipe can carry, the maximum amount of water. So a pipe can carry maximum amount of water obviously when it is running full, right? Or that's what we will do. That's what we will calculate. What is the full capacity of this pipe? And we have to use the Manning's equation. Since this one is FPS system, that is the equation. And after doing all the calculation, we got 2.26 cubic feet per second, which is obviously less than 4.65 cubic feet per second. So obviously this pipe is not working. Now, if you look at this equation, you will see I used S naught, but the original equation was SF. So when we can use S naught instead of SF? Only when we have the uniform flow, right? That's what we learned from our uniform flow part. So we will assume that inside the pipe there will be uniform flow so that we can use the S naught instead of SF. Okay, so obviously that 12-inch pipe is not working. So the next one is 15-inch. Let's calculate with that one. From 15-inch we got 4.096. Again, that is not working. So the next one is 18-inch. So for 18-inch, we got 6.7 cubic feet per second, which is greater than 4.65. So yes, this pipe can work, hopefully. So this pipe satisfies the first condition, should be able to carry the peak discharge. Now the second part, we have to check what will be the maximum or what will be the velocity inside this pipe. Okay. So for that one, we will use this chart. You already know this chart. We used that for circular cross section for uniform flow. Again here we have uniform flow and the cross section is circular, so we can use that one. And just to remind you, we have 4 lines in total, 2 lines for velocity and 2 for the discharge. The broken line, that is for n varies with depth, which is not the case for our class example. And all the solid lines, those are for constant n, okay? Now, you can see on x-axis we have V over V full or Q over Q full. So V full and Q full, if you can remember, those are, it's like when the pipe is flowing full, which we got that from our previous calculation, 6.7, and Q is the one what we have from the peak discharge or peak runoff, which is 4.65. So we can get that QP over Q full 0.69. And since we are looking for the velocity, or checking the velocity, so from this ratio, we have to find the V over V full. How can we do that? Let's watch. So since QP over Q full is 0.69, I will draw a line this way. And since I'm looking for a value for the velocity, I will go from this point to this point and then here. So though it's a little bit more than 1.1, but if you do that by yourself, you will get 1.1. So VP over V full, that P is actually for peak. So V peak over V full is 1.1. Okay. Now, since VP over V full is 1.1, we need to know what is V full. So V full is Q full over A full. And we know V full was, Q full was 6.7, and for A, pi r square. So finally we got 4.17 feet per second. Obviously that is in between 3 and 15. So this diameter actually satisfies both conditions. The first one is it can carry the peak discharge. At the same time, it can maintain a velocity which is in between the minimum and maximum permissible velocities. So this diameter is the perfect diameter for like this sewer system. So D1 is 1.5 feet. Okay. Now, since we have to find the D2 as well, we will repeat the same procedure and everything, but this time the data will be a little bit different. So again, we will start from step 2 because step 1 is still same. So for D2, if you notice, this D2 is actually getting water from this area, at the same time all the flow from here, right? So basically D2 is getting flow from area 1 and area 2. So area 2, that is the flow, and for area 1 the flow is coming through this way. Okay, so the drainage area is 12.5 acres. And if you can remember, if we have more than one area, we have to calculate the combined C or weighted average C. So that's what we will do, that we have 2 areas and the combined C is 0.3152. So we know area, we know C. Now the next one is the I. So for I, we had one equation where we have to use the TC values. So for TC values, again, we have to check what are the possible TC values we can get. So the first one is 9 minutes here, it's given. The second one is TC minimum 15 minutes, that is given as well. This time we have one more TC. Just look at this one. For this area, water is coming from this point and it's coming to D2. We already know that. So we have to consider this travel path as well. And how can we do that? We can calculate the travel path time here. So 13 is given, like from farthest point from farthest point to this point, that is 13. And usually within manhole, this is very fast, so we can ignore that time. And from this point to this point, length is 600, and we know the velocity inside that pipe was 4.13. So we can actually get the time, length over velocity, 600 over 4.13. Since that was on feet per second, we can convert that into feet per minute. So basically we will get 15.423 minutes. Like from farthest point to this point, it will take 15.42 minutes. And obviously that is the maximum among these three. So we will use this one as possible time of concentration. So if we use that value here, 15.423, we will get I equals to 4.33. And now we have CIA, and we can get what will be the peak discharge from these two area. In other words, what will be the design discharge for this pipe D? For this pipe number 2, whose diameter is D2. So 17.0602 cubic feet per second. Now, just like the first part, we will do the same thing again. We have to select the pipe size, and we have to make sure that pipe can carry the peak discharge and maintain the limiting velocity condition. Now, if you can look at your class example, for D1, we chose 18, and the maximum value or maximum flow this pipe can carry is 6.7 CFS. So there is no way for D2 we can try this size of pipe. And you can imagine that one as well from other point of view. This D2 that is carrying the water from area 2, at the same time it's carrying all the water from pipe D1. So obviously pipe size D2 will be larger than the pipe size D1. As for D1, we got 18 inch. For D2, I would like to start from 24 inch. Okay, so let's start working on that. So for 24 inch 2 feet pipe, we got 14.346 CFS, which is less than 17.06. So this pipe size is not working. The next one is 30 inch. Okay, let's try that one. Select D2 30 inch, and we got 26.01 CFS. Yes, that is greater than 17.06 CFS. So we can use that most probably. So this pipe satisfies the first condition, it can carry the peak discharge. Now we have to check whether it can maintain the limiting velocity condition or not. So you know what we have to do. We have to find the V over V full value for that QP over Q full. So this time for QP over Q full is 0.66. If we draw that, this one is 1.09 VP over V full. And for step 5, again, that Q full over A full. Q full was 26.01 pi r square, since the pipe size was 2.5, the diameter. So 2.5 divided by 2 is the r. So that is 5.78 feet per second. Again, this velocity that is within the maximum and the minimum permissible velocity within the pipe. So D2, we can select 2.5 feet for D2. Now we have D1 and D2. The very last steps, that will be actually step 6, I guess. So draw the final layout of sewer pipes. So that one was area 1, that one was area 2. From area 1, water is coming through manhole 1, and then it is going through this way. And for A2, water is coming through this way, And D2 is receiving water from manhole 2 and D1. So that is actually the final layout of the sewer pipes for this area 1 and area 2. And that is the end of lecture 32. Thank you for watching this video.